Hi friends, welcome to follow up. In a previous video, we explained problem 2865, beautiful torus 1. So essentially, that problem and the problem here are the same problem, but the only difference lies in that in this problem here, the height of the given array, the length of the given max height array can be as long as 10 to the power 5. So this means that we need to use better time complexity algorithm. So in this video, we are going to explain a solution based on monotonic stack. So monotonic stack is a very classic and very powerful technique. It's actually good to digest. So here we are not going to read through the problem statement and the digest for these examples. Let's directly look at the analysis. So here first I want to use example 3 to do some analysis, and then we want to do the implementation, and then we want to help you digest the procedure. So essentially we want to check for each index, if we use that index as a peak, so how from the left side and the right side, how much we should shrink, right? So then we just need to compare this, find the index or indices corresponding to minimal shrinkage or decrement, and then we do the computation. So because we can use the total sum minus that part. So here I'm going to use example 3 to demonstrate. So the reason is that we have 2 and 2 and 3, 3 and 5, 5. In other words, this unique values repeats. So here, if we use the 3 as a peak, so we want to compute how much we should shrink to the right. So here, because this is 3, here's 2 is okay. Here's 5 and 5. These two 5s should shrink to be 2. So in other words, we want to decrement by 6 together, right? So here 2 is okay, and this 3. So we need to shrink by 1, right? So basically that's the procedure. What we want to do here is that we want to check for, let's see, we want to get two list, left and right. So the thing is, left I will be the left side head sum up and include index I if we're using I as peak, right? So for example here, if we use 3 as peak, to the left up to this one, we're going to get 3, right? If we use 2 as peak, to the left 3 should shrink to 2. So up to 2, we are going to get 2 plus 2, that is 4, right? If we use 5 as peak, so the left hand side should be, so this one should be 2, this should be 2. So we have 2 plus 2 plus 5, that is 9. So if we use the second 5 as a left side as a peak, so because at this one we have 9, so this we just need to add this 5, so we get 14, right? So if we use this 2 as peak, so for the left side numbers we should shrink them all to 2. In other words, we have 4 2s to the left. Here we have 2, so in total is 10. That is this number. So if we use 3 as peak to the left, so because here is a 2, so up to this 2 we have 10, so we just add this 3, so we get 13. So similarly we can do the right? So if we use index as a, let's say we use this index as the peak, then to the right and up to this, including this number, so what's the sum? So here, because there's no indices in the right, so this will be 3 corresponding to here. And if we use this 2 as indices to the right, we need to shrink this 3 to 2. So we have 2 plus 2, that is 4. So here we have 5. 5 is larger than 2 because any and here is 4. So we just add this 5, we get 9. So here, any and here is 9, but here this 5 is no smaller. So we get 5 plus 9, that is 14. And then any at this, if we use this one as the peak to the right, we need to shrink every number to 2, right? So 1, 2, 3, 4. There are 4 2s to the right, and adding these 2 together we get 10. But here 3 is greater than 2, so any of this 3 we get 13, right? Then for each index, if you add the 2 together and then minus the corresponding number in 3, because we include the index, we count twice. So for this index, so the maximum sum will be 3 plus 13 minus 3, so that is 13, right? So for this one, we have 4 plus 10, that is 12, minus 2, that's 12. So here we have 9 plus 14, the minus 5, that is 18, right? So for this one, 14 and 9, so we are going to get a 23 minus 5 is 18 again. So for this one, we have 10 plus 4 minus 2, that is 12. So this last one is 13. So in other words, if we use index 2 or 3 as peak, the maximum sum will be 18. In other words, the indices might be not unique. We can choose different peaks, but the largest sum is unique. So here, the thing is, how should we implement this one to get this left and right in an efficient way, to taking into consideration of this constraint? That's what we are going to do next. So we are going to jump to the coding part, and in between, we are going to explain the monotonic stack logic. And then, hopefully, after this coding part, you can give a brute force walkthrough or check every status by yourself to get a better understanding for the code. So here, I changed the name to be capital A. This is just for convenience. So now let's look at the coding part. First, I'm going to use length A. So this is just for convenience. And then let's initialize this left, right? So we want to set this left. So here I'm going to use a stack. So I just put -1 here. You can interpret this as an index. For the reason is that if I have a number of 3s at the very beginning, 3, 3, 3, 3, so I can at index I. So for example, at index 2 we have 3 3s. So if you compare the previous one, this is 2 minus -1. This is 3. This is just a small technical detail for ease of or convenience of computation. So with that said, we can get a current. Current, let's set it to be 0. So the current is what we want to set at each index. So now for I in range n, right? So for each index, we want to set the corresponding number for this list left. So here, let's use the monotonic stack. Well, length of stack is greater than 1. In other words, besides this -1, we had at least one index. And then we want to check the monotonic stack condition. A stack -1. If the top element corresponds, so we are in this stack, we are going to store the indices. If the top index corresponding to a number which is larger than the current number, then if we want to use the current number as peak, we need to shrink that, right? So let's first get that. So stack pop. So here we want to this J will be the previous indices, right? So this is an let's first write this one. So we want to decrement this current by stack -1, because this is the previous index. So we want to use this J minus this index. This is the number of elements we want to decrement, and then we times this AJ, right? So this is the condition. So afterwards, so we want to update this current to be I minus stack -1, and then times AI, because if we ending at index I, so if it's larger, right? So after we exit the while loop, the stack -1, either stack will just contain -1. It means that all the previous number before I is larger. So in that case, we do the decrement, and then we want to set all the numbers to be AI, right? So if it's not empty, it means that the top index at the stack will corresponding to numbers smaller. We don't need to shrink. And then we, in between, from the stack -1 plus 1 up to this index I, we want to set those numbers to be AI. So this is the procedure. And then afterwards, we need to append this I anyway. And then we want to set left I to be the current. So this way, actually, we get this left set. So let's print this out. This left. So let's here we want to return something. Let's return some just for these check. So we get this 5, 6, 10, 4, 5. This is for example 1. So now let's use this example for our test, just to verify that it confines with our intuition. So we get a 3. Let's compare with this. We get a 3, 4, 9, 14, 10, 13, right? So this is we computed using our our brain, and this is programming result. So this way we get the left, and next for sure we want to get the right. So for the right, let's do this again. So we get 0 times m, right? So we use a stack. So in this one we use -1 for us to do the convenient counting. So for this one, we're going to initialize using the n, right? So current is 0. Basically, this is symmetric. We just from the other direction. So for I in range, so we start from n-1, then ending at 0, and use decrement -1. So then we use the monotonic stack condition. Well, stack length, let's see, is greater than 1, and the stack top element, if it's larger than a I, right? So notice that the stack stores elements or indices larger than the current index I, right? Supposedly. So we are going to get this one, J stack pop, and then we do exactly the same thing. So current decrement. So notice that we know stack stores elements larger than the current one. So we're going to use this stack -1 minus this G, then times AG, right? So after this while loop, so we're going to reset, right? So we're current increment by, so here we're going to stack, let's see, stack -1. So here we use I minus stack -1. So here we stack -1 minus I, then times AI. Again, we're going to append the current index, and we set right at the index I to be current. So now let's print this again. So let's copy this one. So we are going to change this to be right, this to be right, and let's test. So we get right is 13, 10, 14, 9, 4, 3. Let's compare with this one. So we get 13, 10, 14, 9, 4, 3. We are in alignment. So with that said, let's comment out this. So we are in a great position to prepare the return. So notice the interpretation, right? Left is the left side sum, including this I. Right is also the right side sum, also include this I. In other words, count the same number as this index I twice. So we just need to return the -1, right? So what we want to do is we want to return, so we can use comprehension. So A plus B minus C for A, B, C in zip. So left, right, and the original array. Basically, we use the number here in the left, they will plus, this is the plus, right? Then minus the corresponding one. So we just get the maximum one. So that actually forms a solution. So now before we do anything, let's do a test. Yeah, it passes one example. Now let's look at example 1 just for safety before we submit. Yeah, it passes the first one also. Now let's look at the generic case. Yeah, it passes all the cases very fast. So I would see here, this is a very good example for practicing monotonic stack. So actually we have a playlist which contains a number of problems from LeetCode on monotonic stack. If you are interested, you are welcome to check those problems out. So with that said, I guess that's about it for this